G'day, I'm Ollie, and along with my research partner Josh, we've been tackling the field of cricket ball aerodynamics, specifically how a cricket ball swings. Now in this video, we're going to introduce the general principles of why a cricket ball swings, and then show you how we've been collecting our data. Let's start with introducing what cricket ball swing is. And now simply, it's just the lateral movement of the ball with respect to its major velocity. And this video here shows a perfect outswinger. As you can see, the ball's moved to the left of its initial trajectory that would have hit it towards the stumps. Now, let's talk about why swing occurs. As you can see on the figure in the top right, there is a flow differential between one of the sides to the other. Typically, this is induced by the seam being tilted towards one side. This allows for flow to go over the smooth side and be laminar, and flow to go over the rough side and become turbulent. This flow separation differential allows for the net force to act on the seam side of the ball, because the deflection of the wake goes the opposite direction. As you can see on the figure below, the flow streams on one side, the laminar side, come from the smooth surface of the ball, whereas the turbulent side is where the seam is tilted towards. Now, for the testing of our data, we decided to do everything in situ, that being actually delivering the balls and seeing how far they deviated, rather than previous studies which have put cricket balls in wind tunnels to measure the forces acting on the ball. Our facility was custom built for the purpose of in situ testing, that being its length was the same length as a crease-to-crease distance on a real cricket pitch. It also included a lot of padding and protection measures to not damage the balls. That means that we could test new balls in that same condition for longer. As you can see here in the figure, there is PVC piping making the whole frame with net around the side, and you can see one of our cameras which operates the top being held by a tennis racket, and then also the trial number written on the whiteboard here below. So this camera point of view we're seeing now is the rear camera, and then also the top camera captured the bird's eye view, which was able to pick up details such as seam angle, release speed, and initial trajectory. To show you how we were able to extract the necessary parameters from each delivery, we will run through a trial from start to finish, including the video footage and the code operation. Starting now with the video of the two phones which operate either camera. So the one on the left operating the top camera and the one on the right is operating the rear camera. And this is a live footage of one data point. The next stage is the implementation of a specific code we wrote, which is able to extract the necessary parameters from the video footage we just captured. Now, without getting too technical with how the Python code works, I'm going to show you how we can run it and how it's able to extract the parameters such as seam angle and velocity from the footage captured. Starting with running the code, it prompts the user for the file path of the bird's eye view camera. So what I do is I select a particular footage. So let's go trial 28. I copy that file path and paste it in. It then prompts the user for the FPS or frame rate, frames per second, of the footage, so it knows how quickly or how much time is elapsed between each frame. And the frame rate is 120. It then brings up this footage, which is the top camera footage, which I then have coded in a few different user functions which are able to operate the footage. That being toggling the rotation of the screen and also toggling the frame number. As you can see, I'm clicking between the frames here. Now, the first thing I do is calibrate the screen size. So I do that by clicking C and then going on either side of the ball. So what this does is the computer knows how many pixels are between these 2 points. And it also knows that the cricket ball's diameter is 7.2 centimeters. So using that, it's now calibrated the pixels per meter, or meters per pixel, that the ball has translated between each frame. Now I've calibrated it twice to remove error, and we can now move into the locations of the ball. So for each frame, we can click the center point, and these vectors are then drawn, which is used to calculate the release velocity, because the camera knows how much time is elapsed between these 2 points, and it also knows how far that is in meters, so it can calculate the speed in meters per second. So we'll just finish it off for this. Additionally, we can track the seam angle. So this is selected the same way as the calibration. We start by clicking T, and we click, we need to stop tracking the ball. We click one side there, and then on the other. And you can see at the top, probably can't read it, but it says seam angle of 203, which if you then normalize it by 180 degrees, it becomes 23 degrees. And just moving the tracking location back to where it was, we can put it there. So let's save that. The code then prompts for the user to give the file path of the side camera or the rear camera. So we do this in the same way as the top camera. We go and select the appropriate 28, file copy as path. We go back to the code, enter the file path, and it opens it. Now, as you can see, it's opened it in a funny way, and this is why we needed to build in the user function to rotate the screen. And in the same manner, we can track the ball or click between each frames. To start, we can calibrate the first frame. So what we need to do is the same thing. We just click on either side of the ball, and then we click the ball's location. Now this is a bit of a tedious process because there's about 70 frames between the start and finish. So I'm just going to go and skip and towards the end. So after this, we click save again, and it prompts the user for a folder for the file to be saved or the export to be saved. And if I leave it blank, then it just saves it to the same file that the code is in. So I've done that. And then we name the file whatever we want. So let's go trial 28. Click enter, it's done. It's saved it to the code here. So then we can open trial 28, which is just opened. Okay, now we've got an Excel data, which is essentially a 3-dimensional plot. We're only really concerned with 2-dimensional, that being the pitch map of the ball. And we also have frame, time, and then all the 3-dimensional parameters we need. The most important thing now is to work out how much the ball has swung. So to do that, we compare the X position of the ball here with its initial path. Now the initial path is calculated based on a linear trend from the first third of the ball's positions. And then anything after the first third is then counted as deviation away from it. So you can see here the ball hasn't swung that much. It's gone pretty straight, which was expected from the video. So we can use this, and then the final maximum value of swing, or at least the average value of swing, which is pretty much nothing, about 4 centimeters in this ball, as the swing value. Additionally, there are certain tabs for seam angle. As you can see, it's the 203, as I said. Now, depending on which side you click first, it will either be correct or you have to subtract 180. And then we also have the release speed in the first tab, which shows the speed clicks we started. So release had about 104 k's an hour. So these are all 3 of the parameters that I need to track from our data, that being the release speed and seam angle, and then the resultant swing. Now before I finish the video, I'm just going to present a quick summary of an outswinging delivery that I was able to pick up as seen in trial 43. Now I'm just going to play the video of the tracking of the ball. So as you can see, it's heading towards the right and it comes back around. Just play it one more time. And you can see the resultant pitch map of the ball to the figure on the right, where it's heading down the line and it comes back around. And then the maximum swing value at the end, it's about 30 centimeters, which is what you would expect after looking at this footage. So you can see that the code verifies what your visual interpretation would be, and it does it in a consistent manner across all trials. So that's pretty much the process of how we got our data. And then in terms of the trends we've found, well, we're still in the discovery process, and it looks to be that in situ testing provides a lot more insight into the ball's properties compared